Good evening, and thank you for joining us. My name is Jessica Lounsbury with the Office of Alumni Engagement here at McMaster. Thank you all for joining us this evening. I would like to take this opportunity to acknowledge that the land on which McMaster and this webinar is taking place is the traditional territory of the Haudenosaunee and Anishinaabe nations. The territory was the subject of the Dish with One Spoon Wampum Belt Covenant, an agreement between the Iroquois Confederacy and the Ojibwe and allied nations to peaceably share and care for the resources around the Great Lakes. At McMaster, we start our events with a land acknowledgement to show both respect to Indigenous peoples and their enduring connection with their traditional territories and its histories, and as an important step in reconciliation. I would now like to introduce our guest speaker this evening, Dr. Gregory Cousins. Dr. Cousins is an assistant professor in the Department of Mathematics and Statistics at McMaster University. His research focuses on mathematical logic, exploring the foundational aspects of mathematics and its applications. He graduated with an honor Bachelor of Science in Mathematics from McMaster University in 2012, completed a Master in Science in Mathematics at the University of Oxford in 2013, and earned a PhD in mathematical logic from University of Notre Dame in 2019. November 23rd is National Fibonacci Day, a day that honors Leonardo Bonacci, one of the most influential mathematicians of the Middle Ages. The date corresponds to the first numbers of the Fibonacci sequence, 1, 1, 2, 3. So here to discuss the magic of numbers, Fibonacci, and beyond, please welcome Dr. Gregory Cousins.
Hi, everyone. Thank you for the invitation. I really am happy to have this opportunity to speak at an alumni event as a Mac alumni myself. It's really nostalgic to be, first of all, working here at McMaster in the same office that I used to visit as a student, but also to be able to speak to everyone about something as fun as this. So my title is a little bit different than the one advertised, but that is totally my fault. But I will be talking about Fibonacci numbers today, as well as some other integer sequences that are kind of interesting and appear all over the place, and hopefully convince you that it's not just the Fibonacci numbers that are interesting, but there's a lot of interesting math hanging around. But first of all, why don't we talk about the Fibonacci numbers? So let's see if I can switch slides here. So as some of you probably know, the Fibonacci numbers are a list of numbers starting with 0 and 1, and then continuing in a sort of recursive way. So if we say f0 is 0 and f1 is 1, f for Fibonacci, then f2 is f1 plus f0, which is 1 plus 0, which is 1. How about the next one, f3? Well, what we do is we take the sum of the previous two. So f3 is f2 plus f1, 1 plus 1, that's 2. And we continue on adding the two previous Fibonacci numbers to get the next one. So f4 is 3, f5 is 5, f6 is 8, and so on and so forth. So we get infinitely many Fibonacci numbers. As long as we keep adding them, we get a new one, all right? So we build this, what's called a sequence. And in general, we call this a recurrence sequence or a recurrence relation. We're defining these things recursively. And I'll just annotate here, what this means is the nth Fibonacci number can be obtained by taking the one preceding it and the one preceding that and adding them together. This is for all n greater than 2. So long as I should add with f0 equals 0 and f1 equals 1. If we started with different numbers, we would get a different sequence. But somehow these ones are pretty useful. Now, let me move this this out of the way. So there's a portrait of Leonardo Fibonacci. All of the pictures I use tonight are from Getty Images, so they're temporarily open source. Okay, so that's nice. I mean, it's just a bunch of numbers. So What's so special about them? Well, let's talk about it. Well, the Fibonacci numbers, as you probably know, and as we heard from the introduction, were named, I don't want to say introduced by, I want to say named after an Italian mathematician in the Middle Ages named Leonardo Fibonacci. However, Fibonacci only popularized this sequence in his book Liber Abaci, meaning the book of calculations, and it showed up in a example computing the number of rabbits that appear if you start with one pair of rabbits and they breed every other month. Okay, so he sort of proposed this as a sequence of numbers that could be interesting when you were modeling population growth of rabbits. All right. But it actually turns out that the Fibonacci numbers were well known and well studied for a very, very long time before Fibonacci ever mentioned them. In fact, some evidence suggests that they go back almost 1400 years earlier, not to the year 1400 years earlier than Fibonacci, because they showed up structurally in a lot of Indian poetry. So there were a bunch of Indian mathematicians who were studying these things. And after that, they showed up in various places throughout Asia and only really became popular in Europe with Fibonacci's text Liber Abaci. In fact, Liber Abaci, this textbook, was sort of to introduce the Arabic numerical system that we use today to Europe as a successor to the Roman numeral structure that we're still aware of, but don't use as often, mostly because calculating with Roman numerals is very tedious and wasn't very good for, accounting and gambling and things like that. So Fibonacci introduced these and somehow they carry his name today, but in reality, he was just a popularizer. He was still a very good mathematician and certainly one of the most well-known mathematicians of his age. But it's also a bit of a quirk of history that these things carry his name. And it's sort of interesting. The Fibonacci numbers are somehow deeply rooted in popular culture. If you ask, most people, if you've heard of Fibonacci numbers, the answer will be almost invariably yes. But the interesting follow-up question is, well, why do you know about them, or why are they important? What's so interesting about them? And that's a little bit harder to answer. But we'll explore some of it today. So first of all, for some very mysterious reason, Fibonacci numbers appear in something called phyllotaxis. Phyllotaxis is the arrangement of plant structures. I use that very broadly, plant structures. So it can be leaves, it could be leaves on a branch, it could be petals on a flower, or here's a popular example, a pine cone. Okay, so we're going to draw a little bit and you say, okay, well, I don't see how Fibonacci numbers could possibly appear here. Well, let's draw in some spirals. And let's count them, okay? Now, if you're following along, you can probably see there's a bit of a spiral pattern. So let me start right here. And I will follow this spiral. It's not exact, but it's roughly right there, okay? So there's one. There's another one. Here's another one. Here's another one. It goes down to there. Here's another one. There we go. There's another spiral, and that's all of them, okay? So let's number them. So that's 1, 2, 3, 4, 5, 6, 7, and 8. Okay, so there are 8 spirals kind of swirling in the, I want to say, counterclockwise direction, if you think of them moving. But there's also spirals in the opposite direction. Now, the opposite direction spirals are a little bit harder to see. So I'll start in this maybe top corner over here where I've got a 7. So I've got one there, there, like this. Hopefully you're seeing them now. It's a little more obvious when it's drawn in. Like that, like this, like that, like that. Another one there, and one more here. So let's number them. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. Okay, so where's the Fibonacci? Well, let's remember what our Fibonacci numbers are. We've got 1, 1, 2, 3, 5, 8, and 13. So that's a little bit interesting, right? Because we've got exactly 8 spirals going one way and 13 spirals going the other way. Is this just a coincidence? The answer is no, it's not a coincidence. And this sort of phenomenon appears all over the place. I won't do this. This is a picture of a sunflower, but this video is being recorded, so you should try to enumerate the spirals here. So I'll add maybe a couple annotations. Just they're a little bit hard to see. So here are the here's a counterclockwise spiral. And maybe a little bit, not always easy to spot the clockwise ones. But here's a good one. There's a clockwise one. So if you count these, almost certainly they will be successive Fibonacci numbers. So let's say try at home. Do you get successive Now, of course, nature, nothing is perfect in nature, right? So there are pine cones, there are sunflowers, etc., where you will not get an exact pair of Fibonacci numbers. It's very romantic to imagine that it's always perfect. I have a pine cone in my office over here, and it does indeed work for that one, so good. But, not always. But most of the time, it does. Okay, and this seems very sort of mysterious. Like you've got this random sequence of numbers that you've just built successively as you following some rule. And for some reason, it appears in the structure of leaves and flowers and pine cones. It's very strange. So why is this the case? Or why could it be the case? There are lots of theories. Okay, so let's think about what actually happens. So the Fibonacci numbers, I hope you believe, are always getting bigger, right? To get the next one, we add the previous 2. We're always adding these positive numbers, so we get something bigger and bigger. But what about the ratios of successive Fibonacci numbers, all right? Let's compute a select few. So the second Fibonacci number divided by the first Fibonacci number, 1 divided by 1 is 1. Okay, great. Let's skip a few. Let's say the 5th one divided by the 4th one. That's 5 divided by 3. That's 1.66666 repeating. Okay. All right, let's skip a couple. See, looks like it's getting bigger, but let's see what happens. Oh, okay, if I divide the 8th one by the 7th one, 21 divided by 13, right? It drops a little bit. Instead of 1.66666, it drops a little bit to 1.619 ... bunch of other decimal places. And you're like, okay, that's a little bit strange. You might think it's getting bigger and bigger, but let's jump ahead. Let's see what the ratio between the 50th and 49th is. So this is the 50th one. I don't want to read it out loud. I'm not even sure how many. It's something like 12.5 million. And this is the 49th one, right? And the ratio of them, it's not really that much different from F8 divided by F7. It's about 1.618. And it turns out, for those of you maybe who've taken a calculus course, it turns out that the limit as n goes to infinity, as we get really big, of f of n plus 1 divided by f sub n reaches some fixed value. That's for people who have taken a calculus course or seen the movie Mean Girls. So that's very interesting, right? It looks like it's approaching some number, and indeed it does. And we call that number phi or phi, depending on how you want to pronounce it. Unless you're Greek and you can correct me later. I'll say phi or phi. And this number is very much all over the place in pop culture and nature and everywhere. And so fascinated have people been with it over the centuries that it's got a very dramatic name. It's called the golden ratio. Okay. So why does the golden ratio appear all over the place in nature? Okay, well, simply put, we can do something kind of clever. I couldn't make that picture disappear. I'm not sure why. So let's say we draw a circle and we divide it into two segments, okay? And we ensure that the ratio of this guy to this guy over here, the bigger side to the smaller side, yeah, that's fine. A over B is equal to this golden ratio phi, okay? Then this smaller angle, at least approximately, is what's called the golden angle. And it's around 137.5 degrees. That's not exactly it. It turns out you can't get it as an exact value, but it's close enough, okay? And the interesting thing is it's theorized that the golden angle appears in nature because it allows kind of the best packing, the optimal packing of leaves, seeds, scales, and lots of things like that. So scales, for example, if you count the spirals on a pineapple, you also get successive Fibonacci numbers. Or I rather should say, not the scales, but the curls, the sort of spirals of scales. So similarly, you have spirals going one way and spirals going the other way. If you can imagine a pineapple, or if you're lucky to have a pineapple with you, you can imagine how you have sort of curling, spiraling scales. And if you count the ones going one way and the other way, you'll get, usually, if you're lucky, successive Fibonacci numbers. And the reason really simply, or at least it's theorized, is that this allows for the most to be fit in a very compact area. Similarly, for leaves on a branch, if you're somehow looking at a branch, say, from head on, then the leaves typically are coming out at golden angles. Something like that. These are leaves. This is my bad drawing of, these are supposed to be leaves. I'm a mathematician, not an artist. There you go. So that's very unusual. Very surprising. And, you know, why does it appear all over the place in art and music? Very famously appears in the proportions of Dali's Sacrament of the Last Supper. That's more hard to say, right? I think probably at some point there became a fascination with the golden ratio as being somehow very aesthetic. I'm not sure I necessarily believe that it's more aesthetically pleasing than other ratios, but somehow people have become fascinated for it. And so we see lots of artists including it in their work. There's some speculation that Da Vinci used it in the Vitruvian Man, but there is not a lot of evidence to necessarily support that. But Salvador Dali certainly intentionally chose to incorporate the golden ratio into this painting. It's not very easy to see, but you can see that it's divided into various rectangular proportions, and the ratio of this, say, this side to this side is approximately feet. So it appears all over the place. Another, for those who are fans of the band Tool, there's a song called Lateralis that incorporates the Fibonacci sequence, again, intentionally by the composer. I think just out of a personal fascination, not for any particular aesthetic reason. But it's still a fun thing to think about, and it's rather mysterious as to why we are so fascinated with it beyond how it appears in nature, right? Like, what came first, us noticing it appearing in nature, or general fascination with this number? So the Fibonacci sequence somehow shows up all over the place. Oh. And it shows up in other strange areas as well. So if you, for example, stack a bunch of squares together whose successive lengths are Fibonacci numbers, you get what's called a golden spiral. So if I zoom in here a little bit, you can see, let's say, a side length 1. Oh, it's very... Let's make this a little finer. There we go. So there's a side length 1, side length 1, side length 2, side length 3, and now we get a little bigger. And if we take these things and join them by arcs of a circle, so this is a circular arc here, which just means it's a little piece of a circle, right? We can glue them all together and we get a sort of spiral. Now, this is a special case of something more general called a logarithmic spiral. But it's a special one where it has phi as a parameter, the golden ratio. And surprisingly, it shows up again in terms of the swirls we see in pine cones and sunflowers, but as well as various types of mollusk and snails. So this is a cross-section of a nautilus, which is a very kind of unusual sort of squid-like sea creature that lives in a shell. Very, very pretty, but strange. And we see this nice logarithmic spiral appearing there. Okay, so somehow for various mysterious reasons, and we've made lots of theories and we've built lots of models, the golden ratio and the Fibonacci number appear in nature a lot. And we think it's mostly to do with, as I said, tight packings of things, optimal packings of things, how much can we fit into a small space, things like that. But that's just our best guess. And I'm not sure there will ever necessarily be a perfect answer, but I think if it drives people to be curious about mathematics, then that's fine with me. So the Fibonacci numbers are fascinating. They're very interesting. They show up all over the place. But I want to take a little bit of time to kind of advertise other integer sequences. So the Fibonacci numbers are definitely very interesting, but they're not the only Fibonacci number or the only sequences of numbers that are interesting. And in fact, mathematicians have been studying integer sequences more generally for hundreds, if not thousands of years. So what do I mean by integer sequence? An integer sequence is any list, as we had with the Fibonacci numbers, A0, A1, A2, possibly going on and on, where as long as each of these entries in the list is an integer, that is a whole number, positive or negative, we call that an integer sequence, okay? So I would like to take just a few minutes to look at a few interesting ones. All right, so the first one I want to look at are the so-called triangular numbers. So the triangular numbers are, simply put, the number of dots you need to make a full triangle, okay? So here are the first 6. So 1 dot, we think of that as a triangle just on its own. To make a triangle with the next size up, it takes 3 dots. The next size up takes 6 dots. You notice if I delete, let's see, if I delete one of these dots, all right, like so, I no longer have a triangle. So I really need to ensure that all those dots are there, okay? To make the next one, I need 10, and so on and so forth. So these are the first 6, and you can try to figure out what is, so exercise, ooh. I'll say exercise for you, if you're curious, what is the 7th triangular number? And you can figure this out just by drawing a whole bunch of dots, right? And you can even figure out a general formula, right? If we notice this bottom row has 6 entries, and the next row must have 5, then 4, then 3, then 2, and then the top one has to have 1. So in fact, you can try to show that the nth triangular number is just the sum 1 plus 2 plus 3 plus dot, 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 all the way up to n. Okay? And if you really want to work hard, you can notice, you can do something rather clever, that if I multiply this thing t sub n by 2 times t sub n, then this is the same as 1 plus n plus 2 plus n minus 1 plus dot, 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 and I go all the way to n plus 1. All right. And this is just n copies of n plus 1. And so the nth number, I'll move this over here. Let's squiggle over there. So t sub n better be, I've got a formula now, n times n plus 1 divided by 2. it's sort of funny, this observation that you can do this sort of trick to add these things up was famously done by a mathematician named Gauss when he was in elementary school. His teacher was very tired of hearing students talking, and so he said, okay, add up all the numbers from 1 to 1,000, thinking it would take them many hours or whatever to figure out how long to do it. And then this mathematician Gauss put up his hand right away, and he did it in just a few seconds, and he did this trick. So anyway, triangular numbers are also related to packing circles. So how tightly can you pack, say, circles into a fixed shape? And they're also related to packing of spheres, but we call those tetrahedral numbers. And you can imagine, if I can draw for a little bit, that a hexagon, like a stop sign, right? A hexagon, this is not a very good hexagon, but a hexagon nevertheless can be divided into a bunch of triangles. Like so. And so it's actually hypothesized that triangular numbers are also related, in terms of packing things into a tight area, to the reason bees make honeycombs of a certain shape, which are hexagons. So these appear in nature somehow too. Okay. And here's another interesting property of triangular numbers. Here's a question. Suppose you have 10 people in a room, okay? And everyone shakes hands. None of them have met each other. They're all being introduced to each other for the first time, and they all shake hands with each other, okay? How many handshakes happen? 10 is a little bit of a big number, so that was kind of mean. But let's see. If there is one person alone in the room, just one person, all right? Let's call him person one. How many handshakes happen? 0. Okay, there's no one to shake hands with. What if there's 2 people in a room? How many handshakes happen? Well, they're only meeting each other, so 1 handshake. Let's see, I can draw a hand and another hand. Okay, 1 handshake for 2 people. All right. What if I add a third person? That's P3. Okay. Well, let's see. Person 1 and person 2 have to shake hands. Yes. Okay. Oh, also person 1 has to shake hands with person 3. All right, that's nice. That's 2. And then for everyone to have met each other, person 3 has to shake hands. These are hands, by the way. Has to shake hands with person 2. So that's how many handshakes? 3. So for 3 people in the room, 3 handshakes. 2 people in the room, 1 handshake. 1 person in the room, 0 handshakes. All right. So what if we add one more person? We won't go too crazy, right? So P4, the 4th person in the room, how many handshakes are there? Well, certainly we still have P1 having to shake hands with P2. We certainly still have P1 having to shake hands with P3 and P3 with P2, but now we need the rest of the handshakes. So we also need P2 to shake hands with P4. Okay, great. We need P3 to shake hands with, I don't know why P3's arm is so long, we'll shorten it. P3 should shake hands with P4. And are we done? No, not quite, right? Because P1 has a very long arm, and P1 needs to shake hands with P4 as well. So how many do we have? Let's count them. There's 1, 2, 3, 4, 5, and 6. Oh my goodness, look at that. We've got a perfect correspondence between these things. So if you have 4 people in the room, you need 6 handshakes. If you have 3 people in the room, you need 3 handshakes. If you have 2 people in the room, you need 1 handshake. And if you have 1 person in the room, you have 0 handshakes. So maybe we see a bit of a pattern. If I said, okay, what if we have 5 people in the room? How many handshakes would we need? Well, you might guess the answer would be 10, and you would be correct. And so indeed, if you had 10 people in the room, the answer is 45, which is just the 9th triangular number. And so this is generally a true fact. If there are 2 people in the room, as I said, you only have 1 handshake. 3 people in the room, 3 handshakes. 4 people in the room, 6 handshakes, which is T3, and so on. So in fact, if you have N people in a room, you have to have the N minus first many handshakes. Which is a little bit unusual, right? So somehow, maybe that's not nature, right? But you can imagine, I'm sure you've been in a room where you had to shake hands with a bunch of people, and now you know exactly how many handshakes happen, right? How many handshakes do you have to do? Just N minus 1. Okay, so that's an interesting thing. We've got these triangular numbers, and not to dwell on them, but let's think about something else. And let's start with a question. So let's suppose we have a tree, all right? And let's say it's a special tree for now, where at every branch point, okay, you have exactly 2 branches, okay? And one could ask oneself, let's say I have a tree with exactly n branches, n branch points, all right? How many different types of trees can we possibly have? Let's draw some pictures and try to see if we have some pattern. So if there's 1 branch point, it can only look like one thing. Let's say I've got my branch point and I've got 2 branches, and then maybe I'll give myself some leaves here. All right, so there's only 1 such tree. Okay, well, that's kind of boring. Just 1. What if I allow myself 2 branches? 2 branch points, I should say. Okay, that gets a little bit more interesting. Not that much more interesting, but a little bit more. So I could have something that looks like this. So that's 2 branch points and 3 leaves. I must get better at drawing leaves. Right, that's 1. And I could also have a sort of mirror image. So I could have, there's another branch point and another one. So if we got 2 branch points, I must have 3 leaves. All right, so that's 2. I can have 2. All right, what about 3? Do you think we just get 3 different types of trees? Let's see. Let's draw. Let's try to draw as many as we can. So, okay, I could have this. I could have 1, 2, 3 branches like that. So that gives me 4 leaves. That's certainly allowed, but I don't really have to do that. I could do something like this. I could do, okay, no branch there, a branch here. and maybe a branch here. Still 4 leaves. I'm just going to draw dots as leaves from now on. Okay, so that's a totally different tree. But I could also have done something similar. Like that. Again, 4 branches or four leaves. Or I could have done the sort of mirror of all of these, right? So I could have done, so I'll just mirror them as quickly as I can. Like so. 1, 2, 3, 4, 5, and that gives 5. I don't think I've missed any, but maybe I should double check. Let's see, have I missed any? I don't think so. And you can keep counting this, and you can hopefully imagine that as I allow more branch points, I get more and more trees. It's not just growing like n branch points gives me n different trees. No, as I allow more kind of freedom, I get more possibilities. And it turns out these things are called, the number of such trees are called Catalan numbers. Not after the language, but after a mathematician, E. Catalan, who discovered that they appear all over the place in mathematics, not just counting trees, but just any sort of counting problem, they often show up. And to the point where there are textbooks with 100 problems asking you to show counting one thing is the same as counting these Catalan numbers. So these are very amazing as well. And they also show up in surprising places. And they simply arise from combinatorial problems that mathematicians are interested in. But you can also imagine them as sort of classifying or being able to model branching structures like actual trees or corals or things like that. Branches. Sorry, it's late in the day for spelling. So these are very popular with mathematicians, and I think for good reason. Maybe they're a little less hard or less easy to motivate than the Fibonacci numbers, but they do show up in very surprising places. And then I want to mention one last integer sequence. It's just maybe, I feel like it's maybe as famous as the Fibonacci numbers, but possibly less well understood. And that is the prime numbers. So the prime numbers, just to remind you, are the numbers, the whole numbers that are divisible only by 1 and itself. All right. So probably if you ask someone to list prime numbers, they could 2, 3, 5, 7, 11, 13, 17, 23. This list goes on forever. It's not easy to see why. But this is an old result going back to ancient Greece due to a mathematician named Euclid. So Euclid proved that there are infinitely many primes. And prime numbers are a little bit different from, they're certainly an integer sequence, but they're a little bit different from all of the other ones sorry, I don't know why what I wrote disappears on each slide, but as it is. They're a little bit different from all the other sequences we've talked about because they don't at all follow a predictable pattern. In fact, if one could predict the pattern of the primes, you would automatically become very famous and very, very wealthy. So prime numbers also appear sometimes mysteriously in nature. For example, the life cycles of cicadas are 13 and 17 years and often prime numbers. So they nest underground for a long time and then they emerge and mate and die. And it's speculated maybe so it doesn't sync up with life cycles of various predators, but that's totally speculation. It could just be coincidence. And prime numbers are also essential to you. The existence of really big prime numbers, right? There's infinitely many prime numbers. So there's certainly as large of a prime number as you could possibly imagine, is really how we, for the most part, are able to encrypt secure data. So every time you're using your credit card or you're doing online banking or you're sending a secure email or really anything that involves cybersecurity is relying on the fact that prime numbers exist. All right. So they're very mysterious, but somehow pervasive in your everyday life and really essential. I don't think I could imagine not being able to use my credit card whenever I wanted, or to be able to say tap my phone. The fact that my credit card is somehow stored electronically on my phone and can't be stolen by someone else, you can thank prime numbers for that security. Apologies for those of you who have had your credit card compromised. I'm sure it was no fault of the primes. So anyway, I think I'd just like to conclude by saying that integer sequences in general have fascinated people for a millennia. It's very easy to cook up integer sequences. And to the point where there's a massive online encyclopedia of integer sequences, oeis.org. You should take a look and just play around and search some things up. It's full of information. It's full of fascinating mathematical facts. There's a whole lot on the Fibonacci numbers. So if you want to learn more and maybe just broaden your horizons about integer sequences and mathematics in general, I encourage you to take a look. This is being recorded, so you can definitely navigate there afterwards. But try to explore a little bit and hopefully you gain a new appreciation for mathematics and hopefully it doesn't scare you as much as it does a lot of people. All right, so I think I'll end there. And thank you for listening. I appreciate your attention. And I'm happy to take any questions that anyone might have.
That's great, Dr. Cousins. Thank you so much. Very fascinating. And yes, I definitely do have a new appreciation for math now listening to that. So that's wonderful. I should have mentioned at the start of the webinar too, if you have a question for Dr. Cousins, please type it in the Ask a Question section below. We do have some time to answer a few. So that being said, I'm just going to check the chat here for some questions. So the first question we have, does the Fibonacci sequence represent an evolutionary advantage in nature, or is it simply coincidental?
Yeah, that's a great question. And I think the real answer is that no one really knows. So, it's very difficult to, in mathematics, we like to prove things, like we know they're true. But it's very difficult. This is a kind of evolutionary question, and that's difficult to answer with a certain amount of certainty. So there is speculation. I think I sort of alluded to it, that it does benefit. There is some benefit to having the Fibonacci sequence, and maybe more broadly the golden ratio, appearing, in the sense that it's related to, say, being able to pack things very tightly, spheres or other shapes very tightly into small areas. Or there's been some speculation that branches or tree leaves on a branch are at irrational angles. So the golden ratio is an irrational number. It's not a fraction. But they appear at irrational angles because that's how you minimize overlap between leaves. And so then you gain the most sun, right? But of course, these things are mostly speculative. There have been some models that are able to reproduce these patterns, which are fairly well justified. But it's not necessarily something that's it could totally be coincidental, right? But I think it's very romantic to think that it's not.
Perfect. Okay, looking at question number 2 here. Do you think patterns like Fibonacci or prime numbers could suggest universal mathematical blueprint?
It's a deep question. We need to get like a philosopher in here, or maybe a theologian. I think, I mean, as a mathematician, I think I definitely have a tendency to, you know, put math on a sort of pedestal. And I think that I think it's maybe a chicken or the egg type question, right? Like, the real question is, does the universe follow some sort of blueprint that existed before, or is mathematics rather just a feature of our universe, right? And I would lean towards the latter, that mathematics as a conceptual sort of practice or a framework evolves from like the observations we make of the universe, right? Really, that's how mathematics evolved. We're trying to describe what we see every day, like just doing physics or counting things, right? But we notice that, okay, this formality gets better and better at describing what happens at finer and finer detail. So I think probably what's going on is that we're starting to notice that there are mathematical concepts we've already described that are just appearing spontaneously to us, but are not necessarily spontaneous, right? So
Right. Yeah,
I think,
definitely.
yeah, I know both of these are sort of like non-answers, right? But I think, yeah, I think, what advice would I give to a student who is math phobic? How can a young student learn to love math like me? Well, okay, that's a great question. And I think first of all, hearing stuff like this, seeing stuff, maybe reading things about the Fibonacci sequence and things like that is a great way to start. I think I can tell you, I can talk all night about why people develop math phobia. And I think a big reason is because there's a lot of stigma around just being wrong, which is, I think, the opposite of we should celebrate being wrong, because being wrong is how we learn things. But there's always been this feeling, especially around mathematics, where it's, if you struggle and you get something wrong, it's not that people will say, oh, well, you're just not a math person, right? And I always find that so crazy, right? Like, I don't think there's such things as math people or not math people. I think there are people who have been encouraged and learned to enjoy it and have learned to enjoy the process of being wrong and working hard to understand something, and people who have been discouraged, right? Certainly there are variations in just like ability, but I don't think anyone can realistically say they're not a math person. So to answer your question, I think, the way to encourage a young person is to just enjoy the process, right? Like try to understand what you're doing and take some satisfaction from getting things wrong and then going back and getting things right because you understand it better, right? There's no satisfaction in just everything coming easy. It might be nice at first, but it's boring. All right. So it
Yeah,
doesn't
very true.
matter how much you like mathematics, even if you're someone like me, if you become a professor, you're always just going to run into other mathematics that's harder, right? So just you work harder and harder.
Yeah, and the resource that you provided too as well, I imagine just going and exploring different areas. If something does catch your interest, go and learn more about it. Check out more about
Yeah,
it. Yeah.
definitely. Just be
Uh,
curious. That's it.
yeah, exactly. Be curious. Looks like we have time for one more question here before we wrap up. You mentioned the series related to music. How?
Right. So I would say the series appears in music in a very synthetic way, right? This is what I was saying, especially art. I think again, another sort of chicken and the egg type question, like does it appear naturally? I would guess no. I think their fascination with Fibonacci numbers and the golden ratio and things like that for not necessarily a clear reason. And so for example, I mentioned Tool used it in their song, and I think they used it just because they think Fibonacci sequence is very cool, right? So if you look at the various verses, the number of syllables in each line is successive and then descending Fibonacci numbers. And there's also some speculation that Bach used like the golden ratio and Fibonacci numbers in various compositions. And I think like does it appear spontaneously without the knowledge of the composer? I doubt it. It would be very unusual, right? If we somehow like statistically analyzed all music and somehow there was this pattern to the golden ratio. I don't think that's true. But I do think it's nice that some people love mathematics so much that even as different sort of professionals, say musicians or whatever, they enjoy importing that into their work. And I think it's doing a great service for mathematics as well because it catches people's attention. And so no complaints about that.
Yeah, absolutely. It is very fascinating. And again, thank you so much for taking the time to give this talk this evening. I found it fascinating. I'm sure all of our viewers did too. And like we said, it is being recorded. So if you would like to rewatch it or share it with a friend who may be interested, a link to the recording will be sent out in the follow-up email, which you will receive later this evening. In that email, there'll also be a link to a quick survey. Please take a few minutes of your time to fill it out and share your feedback with us this evening for our viewers. Just one note, our final talk of the exploration series of webinars will take place next Wednesday, November 27th at 12:30, and will be on the opportunities and societal impacts of generative AI today with McMaster alumna Cassidy Bereskin. Dr. Cousins, thank you once again for taking the time out of your schedule and giving us this talk this evening. It was great. We really appreciate it. And to all of our viewers out there watching, thank you so much for tuning in and have a great evening.
Thank you so much.